Hello everyone, this is a video about our final project, Face and Facial Expression Recognition. This is the overall architecture of our project. Basically, we will first do face detection, and then we will use the extracted faces and use a convolutional neural network to do the feature extraction. Then we will use three different techniques, that is encoding, regression, and classification, to do the recognition task. That is face, age, and gender, and facial expression recognition. First, I will introduce about the face detection part. And this is a very simple one. We will use HOG-based detection. For each pixel, we will try to calculate its gradient. We will use Sobel operator to calculate the horizontal and vertical gradient. Then we can use these two gradients to calculate the magnitude and the orientation of the gradient of each pixel. In order to extract features from the whole image, we can separate the image into several cells, and for each cell, we can record the statistical information for all the gradients of pixels in that cells. Then, for a given image, we can use a sliding window, shifting from the top left and row by row until the end of the picture. And for each sliding window, we can use the method that I introduced in the last slides, that we can map each sliding window into a high-dimensional space that is single point. So we can use a classifier, like in our case, we use support vector machine to classify whether it's a face or not. So this is a demo. From the demo, we can see this method is very fast, but there is also a problem. That is, if we cover most of our face, it cannot recognize your face anymore. So we try to use some more advanced techniques. That is the state-of-art algorithm in nowadays, that is YOLO v3. This method works like this. It will first divide the input image into an S by S grid. If the center of a face falls into a grid cell, that grid cell is responsible for detecting that face. Each grid cell predicts two bounding boxes and confidence scores for those boxes. These confidence scores reflects how confident the model is that the box contains a face, and also how accurate it thinks the box is that it predicts. Formally, we define the confidence as the probability of face times IOU. If no face exists in that cell, the confidence score should be 0. Otherwise, we want the confidence score to equal the intersection or union, that is IOU, between the predicted box and the ground truth. Each bounding box consists of 5 predictions, that is X, Y, W, H, and confidence. The XY coordinates represent the center of the box relative to the bounds of the grid cell. The width and height are predicted relative to the whole image. Finally, the confidence prediction represents the IOU between the predict box and any ground truth box. So for each grid cell, we can get a probability that is face in that grid cell. Then we can just sort all the predict bounding box and pick the bounding box set with the largest value. And based on this idea, we can derive this loss function, so we can transform the detection problem to a regression problem. And this is a demo based on YOLO.
Okay, this is face and facial expression recognition part. We use two datasets. The first one is FER 2016, from which we mainly choose 5 kinds of single expression, each of which is a 48 by 48 pixel grayscale images of face. The number of each class images is shown in the figure. The faces have already been automatically registered so that the face is more or less centered and occupies about the same amount of space. We can see the distribution of the data in the figure below. Apart from that, we found another popular and relatively common used dataset called Extended CK Plus dataset. It includes about 500 sequences of 100 poses. Each sequence begins with a neutral expression and proceeds to peak expression: surprise, sadness, anger, happiness, and neutral. As every single data is a sequence of expression, we pick up the last few images of each sequence as the training data, so we have 2000 images as the training data. We can see from the exploration of the FER dataset, the number of images in discussed class is significantly less than other class. It may lead to a potential problem, so we decided to do the data augmentation. As we said before, if the number of data in some class is not enough, the model is likely to be overfitting. It is a common knowledge that the more data an algorithm have access to, the more effective it can be. Even when the data is of lower quality, algorithms can actually perform better as long as useful data can be extracted by the model from the original dataset. We basically rotate the original image by a small angle, flip them up and down, right and left, and add some small scale noise to the image, and add this image in our training set. As we know, the facial expression is a fine invariant. The facial expression has nothing to do with the perspective we view the image. Another method we use to avoid overfitting is batch normalization. It normalizes the feature by the mean and the variance computed within a mini-batch. The stochastic uncertainty of the batch statistics also acts as a regularizer that can benefit the generalization. However, when the dataset is not so large, we cannot support large batch for gradient descent. A small batch leads to inaccuracy estimation of batch statistics and increase the model error dramatically. Trapped in this problem for a long time, we found a paper called Group Normalization. It presents group normalization as a simple alternative to batch normalization. We can see from the right figure, batch normalization calculates the mean in n dimension, whereas the group normalization divides the channel into groups and computes within each group the mean and variance for normalization. Group normalization's computation is independent of batch size, and its accuracy is stable in a wide range of batch size. According to the paper, the error of the batch normalization and the group normalization is shown in the figure. For the architecture of the neural network, in milestone 2, we use the network in the left figure, and in milestone 3, we switch it to the right one. This is a parameter visualization of our network. This figure is actually a final product of several histograms of learned parameters layered together. Each slice in the histogram figure is a single histogram. The slices are organized by step. Older slices are farther back and darker, while the newer slices are close to the foreground and lighter in color. The y-axis in the right shows the stack number. Compared with the model parameters in the milestone 2, the trend of the parameter is obviously different from the milestone 2. We pick up one convolution layer. In the figure above, the parameters in this layer is mainly distributed in a small range, which means the weights are similar. From the figure below, we can see that the parameters are distributed relatively widely, and the weights are larger, which means the model learned what features are more important and gave more weights to them. As I use the L2 regularization, the weight is larger but the loss is smaller, which means the accuracy is improved. To get more insights of the neural network, we visualize some features extracted by the CNN in different layers. In milestone 2, we can see that The first layer basically grasps the global feature of the images, such as the outline. As the layer becomes deeper, it extracts more abstract feature of the image. In milestone 3, we subtract the mean pixel value of every image and just show the difference. The black part means this part is the same as the main image, while the white part refers to the difference. We can see that as the layer becomes deeper, it extracts more abstract feature of the image, and the difference mainly lies in mouth, eyes, which controls the facial expression. Then, this is the result of our recognition. On cargo change dataset, we get accuracy about 67, and on the CK plus dataset, we get accuracy near 19%. Here is the demo.
Okay, for the face recognition part, in the previous method, we have explored different configuration of ConvNet, and we found with the growing of depth, we can achieve a higher accuracy. But if we want to recognize a new people that is not originally in the database, we have to retrain the network, and it is a waste of time and also a waste of efficiency. So, is there any more simpler way to do that? And we found this paper. The basic idea of this paper is try to encode every image into a vector. So the similarity between each image can be calculated as the distance between each vector. And based on this idea, we implemented the idea by two identical convolutional neural network. And the output of the final layer is the vector that we want. And we can input the image and use the vector of the last layer as a point in a high-dimensional space. And our objective is try to make the distance between the same group and minimize the distance between the same group and maximize the distance of the instance of the different group. So we can derive this cost function.
For age and gender recognized, first I will introduce the dataset. This time we use the dataset found in Wiki called Wiki Gender and Age Dataset. This dataset contains 60,000 images of most popular actors on the IMDb website. Apart from the image, their information such as gender and age are also provided. Thus we can use the dataset to train the neural network. We choose 40,000 images for training and 5,000 for test, and resize the image to 128 by 128 as the pre-process. The figure below is the distribution of the data. We can see that the majority of images are distributed between the 20 and the 40. Then here is the architecture of our neural network. This time we use 4 convolutional and max pooling layers, and just use 2 batch normalization layers after the last 2 pooling layers. It is because that we have enough data to avoid overfitting, and based on the results of milestone 3, the number of normalization layers does not have a dominant influence on the accuracy. These layers work for feature extraction. Then the fully connected layers are much different from previous works. In this architecture, there are 2 parallel fully connected layers using the same input. The first part is used for gender recognition. In this part, the final output is the probability of being a male or female. It is a classification problem, while the second part mainly deals with the age recognition, which is a regression problem, and the final output is a predicted age. We transform it to an integer. Next is the results of our neural network. The figure above is the loss and accuracy of the gender classification. We can see that the accuracy is about 19%. The figure below is a loss of age regression in training process. Then here's a demo. For the future work, in face recognition, when the face is covered or we take off the glasses, the accuracy will drop. After doing a survey of this problem, we find a solution called dictionary learning. The main idea of dictionary learning is factorizing the training dataset matrix to a product of a dictionary and a sparse representation. Each column of dictionary is an atom, which means that is a certain feature. And each row in the sparse coding matrix X is a sparse coding of corresponding training data. For example, the dictionary times the ith row of the matrix X is the approximation of the ith training data. Thus, each data is a linear compilation of all features. For test data, we can first use the L1 minimization problem to calculate the sparse coding of this data. Then there are two ways to calculate its label. The first way is to use the sparse coding matrix X to train a classifier and apply this classifier to this sparse coding. And the second way is to calculate the distance of the new coding to every row in the X and use the k-nearest label to vote for the new label.
And this is the reference. Thank you.